All right, hello everybody. Today we're going to cover over section 2.1. These are in your slides, so I'm just going to kind of go through them as I normally would if I was in class. So follow along, fill out your worksheet as we go, just so that you have your notes, and let me know if you have any questions. So today we're going to start talking about the nature of matter. So what is matter? How does it work? All those kinds of things. So the first thing is, what is an atom? An atom is the smallest particle of an element that has all the characteristics of that element. So when you look at the periodic table, every element on the periodic table is a certain atom. And we're only talking about that atom when you look at that certain element. So there are 92 of them that are naturally occurring here on Earth, meaning we can find them all over and they are making up everything we see around us. There are 20 that are about man-made. Those are the ones generally found that are separated. Those are called the lanthanides and actinides towards the very bottom of the periodic table. Most of those are made in a lab by scientists by throwing atoms together. We generally don't worry about those too terribly often. 4 basic elements that make up more than 96% of humans is carbon, which is the letter C, hydrogen, capital H, oxygen, capital O, and nitrogen, which is a capital N. So carbon, hydrogen, oxygen, and nitrogen are the basic makeup of a human. So we are made up of mainly those 4 atoms. There are a few others as well, but those are the main 4 that create life. In every atom, there's something called the nucleus. So the nucleus is the atom has protons and neutrons, which make up its atomic mass. So in the very inside, we have this little ball here. That is the nucleus. It contains those protons and neutrons. Protons, we'll talk about here in a second, have a positive charge, and the neutrons have no charge. Outside, we're going to have our electron cloud that goes around the nucleus to be able to create whatever atom we're looking at. So this we'll need to know is the 3 parts of an atom. So the 3 parts of an atom are protons. We can represent that by a plus sign because they have a positive charge. Those ones are always found in the nucleus. So these little guys in blue here, those would be your protons. A neutron, represented by a 0, or sometimes they're just left blank, like this guy down here. Or you'll often see it with a lowercase n or a capital N found inside of them. Those guys are neutral in charge, meaning they have no charge whatsoever. They're just kind of there to help give the atom some mass. And again, also found in the nucleus with the protons. Our last part is electrons. Electrons are these little green guys on the outside. Those are negatively charged particles, and they're found orbiting the nucleus. They never go inside because we know opposites attract. They're going to hover around so that they don't stick together. Now, the interesting thing about electrons is that they are actually 1/1084th of a mass of a proton. So they are very, 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 very small. We actually don't count them even inside the mass of the overall atom because of how small they are in general. We really just focus when we're trying to figure out the mass of it is looking at these 2 right here, because we use the mass to help us figure out how many neutrons we actually have in each element. Now, when we talk about an element, elements are everything is made up of elements and a substance that cannot be broken down into a simpler substance. So when you see an element and it says hydrogen, for example, so like this guy right here, when you just look at the hydrogen element, it's just hydrogen. That's all it is. We can't break that down any further. I guess if you wanted to, you could break it down to protons, neutrons, and electrons, but then that's focusing of what makes up that hydrogen. But we can't break that down any further. We have something called the element symbol, which each element has, which is either 1 or 2 letters for an abbreviation of the name. So on your periodic table, you should be able to see this same picture that I have right here, or a similar one. You'll see some of them have 1 symbol, or 1 letter. Some have 2, so just like the one below hydrogen, which is lithium. Lithium is Li. It just depends. Some have 1, some have 2. It's no certain rhyme or reason. They just decided to abbreviate them all differently. There are a few that their names do not go along with the letters that are given to them. So for example, Mercury is a popular one. Mercury is Hg, found right here in the periodic table. It should be number 80, its atomic number. It's actually Hg, even though we would think, why wouldn't it be Me or something like that? Honestly, I don't know. They just decided that's why Mercury is going to be Hg. Same thing with silver. Silver is not too far away, number 47 on the periodic table. It's Ag. Another common one, the one right below it, Au. That's gold. So, yeah, most of the time their names and their symbols match. So, like hydrogen's a capital H. Lithium is Li. But there's a few, like sodium and mercury and gold, and those are kind of the main ones that are standing out to me right now. Those ones, they don't necessarily match their name. Okay, so let's talk about our periodic table some more. So when you look at your periodic table, you're going to see a box on every single section. There's going to be a letter or two, the name, the atomic number, and an atomic mass. Each periodic table is laid out a little bit differently. Generally, you're going to find the atomic number found towards the top left-hand corner. The atomic number is going to tell you how many protons you have in that element. So if you're ever wondering, how many protons are in lithium? You can just look at lithium. It says it is the number 3. So there's 3 protons. Same thing with oxygen here. Oxygen is number 8 on the periodic table, meaning it has 8 protons. So it's a helpful way for us to be able to lay out our periodic table and also identify it. Then we can also look at the atomic mass. The atomic mass is protons plus neutrons. So for example, oxygen it says 15.999 on most periodic tables. A lot of times we just round that up to 16 just to make our lives a little bit easier. So that gives us the atomic mass. That tells us how many protons and neutrons we have inside of the atom or inside the nucleus of that atom. We are also able to find the element symbol. So that tells us what element we're dealing with and the abbreviation with it and the name. So that's kind of how to read a periodic table. Now we need to be able to figure out how many protons, neutrons, and electrons does every atom have. And we could do that by looking at these symbols up here and doing just a little bit of math. Most of it's mental math. It shouldn't be overly difficult, but you can always use a calculator if you need to. All right, so the first thing is trying to figure out the protons plus neutrons gives you the atomic mass. So that's helpful when we're trying to figure out how many neutrons are in our element. So for example, if we start with our very first guy, hydrogen. So hydrogen is number 1 on the periodic table. Hydrogen has 1 proton. And we know that because it is number 1 on the periodic table. Well, one helpful thing is that the number of electrons always equals the number of protons because they are balanced, and to be balanced, the positive and negative charges have to balance out. So that means we have 1 electron inside of our atom as well. Now we have to figure out how many neutrons we have. Well, we have our equation here of protons plus neutrons equals the atomic mass. So if we have the proton and we have the atomic mass, we will then be able to solve for our neutrons. So if you look, you'll see a number similar to this. Sometimes it's in the right-hand corner, sometimes it's found on the bottom. A lot of times on our periodic tables in class, they'll be highlighted in red. But they'll say, it should say 1.008. That is the atomic mass of oxygen or of hydrogen. So what we're going to do is we're actually going to do a little bit of math. So we're going to take the atomic mass, which is 1. We're just going to use the whole number there, minus the number of protons, which is 1. 1 minus 1 is 0. So that means there are 0 neutrons in the hydrogen atom. All right, let's move on to the next one. We have carbon. Carbon is the letter C on the periodic table, and it is number 6. So it's atomic number 6. Since it is atomic number 6, that means there are 6 protons. Since we have 6 protons, that means we have 6 electrons, so that they balance out. And now we need to solve for how many neutrons. Well, if you look on the periodic table, you'll see it'll say 12.011. We're just going to use that 12. So 12, which is the atomic mass, minus the number of protons, which we said was 6. 12 minus 6 is 6. So we have 6 protons, 6 electrons, and 6 neutrons. All right, let's try the next one. We have aluminum. Aluminum is number 13 on the periodic table, so go ahead and find that one. And I want you to try and fill out your worksheet for aluminum. I'm going to give you a few seconds. So if you need to, just pause the video. Okay, so let's solve for how many protons we have in aluminum. So since it's atomic mass number 13, that means we have 13 protons. That also means since we have 13 protons, we have to have 13 electrons. All right, now we need to solve for the number of neutrons. So if you look, it is 26 for its atomic mass. So 26 minus 13 equals 13. All right, let's do silver now. Silver is Ag on the periodic table, so that's one of those weird ones. And let's see, since it is number 47, atomic number 47, that means there are 47 protons. Also means since we have 47 protons, we have to have 47 electrons. And now we can solve for how many neutrons we have. So silver is 107, which is its atomic mass, minus the number of protons, which is 47. So 107 minus 47, you should get 60. So there's 60 neutrons in every silver atom. All right, and our very last one is uranium. That's the letter U. It is found at the very bottom of your periodic table in the section that is separated. Uranium is naturally occurring here on Earth. It is not man-made. So uranium is number 92. So atomic number 92 on the periodic table. So that means we have 92 protons. That also means, since we have 92 protons, we have to have 92 electrons. And now we can solve for its number of neutrons. So we're going to take the atomic mass, which is 238, minus 92, the number of protons. 238 minus 92, we get 146. So that's how you solve for your protons, neutrons, and electrons. Again, protons just equal the atomic number. So this number up here. The number of electrons equals the number of protons, so those numbers should be the same. And to solve for neutrons, we take the atomic mass minus the number of protons, and that's going to give you your neutrons. So let's keep moving on. Okay, now let's talk. Now that we know we have protons, neutrons, and electrons, now we have to figure out, well, if protons and neutrons are found in the center, how do we arrange our electrons? So we have something called energy levels when it comes to our proton, or our atoms. So when we do it, there's a very specific order that they must go in, and this is very, very, very important. So they follow in this order. It starts with 2 in the inner ring, then we go 8 electrons, then we go 8 electrons, and then it goes 16, and they get bigger and bigger as they go. We're not going to go anything above 8. So we always have to fill from the inside ring to the outside ring. That's because we need to fill those energy levels closest to your protons and neutrons first before we can move out. So for example, let's say we're dealing with aluminum again. So that's atomic number 13. That means we have 13 electrons to deal with. So the first thing we're going to do is we're going to fill in our inner circle. And again, the first one can only have 2 electrons. So I'm going to fill it in. I'm going to put 1 electron here. Again, you can represent it as dots. A lot of times you'll see me do this, where you'll see me use an E with a little negative sign. That is the same thing as an electron. Or sometimes people will draw like a circle with a little line in the middle to show an electron. So just to make it easy and easy to read, let's just use dots for now. So we go 1, 2. Now that first ring is full. It can only hold 2 electrons. So now I'm going to move to my next ring, which can hold 8. So now I'm at 2. So I have 3, 4, 5, 6. So I'm up to 1, 2, 3, 4 on the outer ring. And I've only used 6 electrons total. So I got to keep going. So I'm at 6, 7, 8, 9, 10. And now I have 1, 2, 3, 4, 5, 6, 7, 8 electrons in that second ring. Now I need to move out even further. So I have 10 total. I'm going to keep moving outwards. 11, 12, 13. So now I have all 13 electrons shown inside of my rings. And I have a couple extra spaces left that if I needed to add electrons, I could. I could also take electrons away, so we would erase some of these. But this is the easiest way to show your electron energy levels. So the most important part, the first ring here can only hold 2 electrons. Your next ring can hold only 8 electrons. Then you have to move outwards to your very last ring, which can hold, again, another 8. If it doesn't have a full 8, that's okay. It can stay like that. But you have to fill the inner ones first before you can put them on the outside. If you have questions on that, let me know. Okay, now let's talk about something called isotopes. Isotopes are interesting because they're elements with the same number of protons, but they have a different number of neutrons. So this is going to give us a different type of mass for this same element. So that's why when we talk about the atomic mass is just the average of all of the different types of that atom. Because some can weigh more and some can weigh less. So for example, we talk about carbon. Carbon is a common isotope that we deal with. And we have, for example, carbon-12, carbon-13, and carbon-14. Each of these are different based off the number of neutrons that they have. So carbon-12 means it has 6 protons, but it has 6 electrons. Just like what we talked about earlier, because we took 12, the atomic mass, minus 6, and we got 6 neutrons. So in that example, we dealt with carbon-12. We can also deal with our carbon-14, which means it gained an extra 2 neutrons. It's still carbon because the number of protons stayed the same, but it's just that mass changed because we gained a few extra electrons. Or sorry, gained a few extra neutrons in our atom. And it just changed the weight. We could also only gain 1 extra neutron. And sometimes we can gain 2. It just depends on the different size of each isotope. So that's why, again, the atomic mass is an average. And we use those isotopes for different things. A lot of times we use it for decaying to try and figure out the age of something. All right, let's talk about chemical compounds. Compounds are substances that combine two or more elements that are chemically combined. So we deal with compounds quite frequently, almost daily, or pretty much daily. When we combine two of these elements or more together to form whatever substance we're dealing with. So the physical and chemical properties of a compound are usually very different from those in an element in which it's formed. So just because it's made up of two elements, it doesn't mean it's necessarily going to behave like each individual element. So for example, we have sodium and chlorine. So sodium is Na, chlorine is Cl. They are both poisonous to use individually, but combined, they become NaCl, or sodium chloride, which is table salt that we use pretty much every day. So two things that are naturally poisonous on their own are combined together to make something we eat all the time. So they don't follow their kind of individuality or individual selves. When they combine, they create this brand new substance. Something important for biology, though, is we have to talk about organic versus inorganic compounds. So we have organic compounds contain carbon and usually derive from living things. So if anything is going to be considered living, it needs to have carbon in it. If it is inorganic, it does not contain carbon. So those are your non-living things. So down below, we have several different compounds, and we have to decide which ones are organic and non-organic. So glucose is, the chemical formula for that is C6H12O6. Water, we should know, is H2O. We have carbon dioxide, which is CO2. Again, the subscripts are telling you how many of each atom you have. We have sodium chloride, which we just talked about, is NaCl. We have hydrochloric acid, which is HCl. And then we have carbon monoxide, which is CO. So carbon and oxygen. So we got to go through and we got to figure out which of the following are organic. And again, for anything to be considered organic, it has to have carbon in it. So we have glucose, which has carbon in it, our lovely letter C. So glucose is organic. Water has no carbon in it, so it is inorganic, meaning it is non-living. We just talked about that in our last chapter. We have carbon dioxide, has our lovely little C in it. That is organic. It comes from living things. We breathe out carbon dioxide. Sodium chloride, NaCl. Even though we see a C here, that C is attached to that L. So that is chlorine. That is a totally different element than our carbon. So that is inorganic. We have hydrochloric acid, which is a very strong acid. That, again, has the C there, but it's attached to an L, so that is a totally different element. So that is inorganic. And then we have carbon monoxide. Carbon monoxide has our lovely little carbon there. That is organic. Carbon monoxide, a lot of times we'll see that coming out of furnaces. And a lot of times we'll hear that within carbon monoxide poisoning. So it is a naturally occurring compound. Now, when we talk about that, when we talk about compounds, we also talk about bonding. So bonds are two types that are ionic or covalent. So we have two types of bonding that we have to worry about. And we also create something called ions. Ions are positively or negatively charged atoms. Oftentimes we deal with those when it comes back to this ionic compound. So ionic compounds have a net gain or loss of an electron on the outer energy level. So we are going to either give up or take in an electron. Covalent bonds are sharing of electrons from their outer energy level of two elements. So an example would be water. Water is covalently bonded together. So some ways that I've taught kids before to remember the difference between ionic and covalent is ionic has I want it, I take it, because we gain or lose electrons. So I'm going to take something. If I want it, I take it, and it's going to change the number of electrons. And then they bond together because one becomes more positive, one becomes more negative because they just lost or gained an extra electron, and they stick together. Covalent, this prefix co, we generally hear of together, like a co-ed soccer team, meaning there are both boys and girls. Together. So covalent means together they're going to share these electrons, and the electrons will move freely between the two elements. So let me show you an example of what that would look like. Okay, so we have sodium chloride. That is an ionic bond. Sodium is number 11 on the periodic table, meaning it has 11 of our electrons and protons. So sodium, again, is Na. And we need to draw the number of electrons. So I'm going to draw an electron cloud around it. So we're going to have 1, 2. That energy level's full. So we're going to keep moving on. And again, I need to fill it to 11. 3, 4, 5, 6. Well, I got to keep going because I only have 4 in that ring. 7, 8, 9, 10. Okay, I have 8 in that ring. That means I need to draw another ring. And 11. Okay, so I have all 11 electrons taken care of. Now we need to go to chlorine. That's Cl. That is number 17 on the periodic table. Has atomic number 17. So that means it has 17 electrons. So we draw our ring. 1, 2. Draw our next ring. 3, 4, 5, 6, not full yet, so we got to keep going around. 7, 8, 9, 10. That ring is now full. We got to go to our last ring. So now we're at 10. I need to go to 17. So 10, 11, 12, 13, 14, 15, 16, 17. So the reason I went the other way this time is just to make our drawing a little bit easier to see. Okay, so now we see on the outside, this sodium has 1 extra electron here. And for everybody to have a buddy on this side, this guy is missing somebody. So what's going to happen is this electron from sodium is going to be taken and given to chlorine. So sodium, since it lost an electron, is going to become more positive because it lost an electron. Chlorine, since it gained an extra electron and electrons are negative, is going to become more negative. Since positive and negatives attract, they're going to squish together and create sodium chloride as one big compound. So that is an ionic compound. Now, for water, which is covalent, so let's label these. For covalent, these electrons are going to be shared. So I'm going to start with oxygen first because it has the most number of electrons. So we have compared to hydrogen. So we have oxygen in the middle. Oxygen is number 8 on the periodic table. So it has 8 electrons. So I'm going to draw the 8 electrons. So we have 1, 2. Draw my next ring. 3, 4, 5, 6, 7, 8. Again, the only reason I drew it this way was to make our drawings just a little bit easier. Okay, so I have 2 empty spots here where they don't have buddies to move on to the next ring. So what's going to happen is each side is going to gain a hydrogen. And hydrogen has 1 electron. That means these guys here are going to slide over and they're going to attach, if it'll let me. Oop. Well, it's not going to let me slide that one over, but you get the picture. It's going to slide over and these electrons are going to share between all these 3 atoms. So they're kind of keep moving in and out and keep going back around and be shared between them. So again, the difference between ionic and covalent. Ionic, I want it, I take it. I took that electron from here, from sodium, gave it to chlorine. Sodium became more positive, chlorine became more negative, and they stuck together. Covalent bonds, on the other hand, they're going to share those electrons nicely between the 3 or 2 elements that are being bonded together. So they're going to share those nicely together. Another helpful thing to know is ionic bonds are the strongest bonds because we're giving up those electrons. That positive and negative charge hold them together so tightly. While covalent, since they're sharing, it makes it just a little bit weaker bond. So it doesn't take as much energy to break those guys up. All right, now let's talk about a molecule. So a molecule is the smallest unit of most compounds. So what we just drew, that would be considered a molecule because it's just one single molecule of water, which is H2O. Within that molecule, we have these van der Waals forces. A Dutch scientist, which was van der Waals, he described the bonding phenomenon, the attractive forces between positive and negative regions that pull the molecules and hold them together. So we know there's these positive and negative particles that are trying to pull each other together, but then electrons are trying to repel each other, and protons are trying to also repel each other. And we're like, how is this all staying together? Well, these attractive forces within them and within each individual molecule force these water molecules to stick together. So these attraction forces are so strong in between, even though they are wanting to repel each other because they both have these electrons on the outside and water molecules stick together really well. These van der Waals forces force them to stay together and make water droplets and make water flow nice and clean. So van der Waals forces we can thank for keeping our water together. We also use a lot of kinetic energy. So kinetic energy is the energy of motion. So anytime you are moving, it is considered using kinetic energy. So Robert Brown in 1927 used a microscope to see small objects in continuous motion. So we were actually able to see things moving and swimming around using their kinetic energy all the time while observing the pond water. So he came up with this idea called Brownian motion, which is the movement of molecules. So molecules like to bounce and move around. It really depends on the temperature, is how fast, and also what they're made out of how fast they're going to be moving around. Gas particles move the fastest because of how their mass and how fast the movement is between them. Liquid is in the middle. It moves still pretty quickly, but the forces aren't as strong to keep them together. And then even solids do move. So any solid object that we deal with on a daily is moving. It's just moving at such a slow rate that we just don't notice it. So that Brownian motion explains how those molecules move. On the slides, there is a video you can watch. So if you have more questions on that, go ahead and pop over there and take a look at the video, and I'll explain it just a little bit more. Now, that is our notes for today. So I know we covered a lot. So main things to take away from today. 1, what's an atom? It's the smallest particle of an element. And there are 92 that occur naturally and 20 that are man-made. Inside every atom, there's a nucleus. The very center part made up of protons and neutrons. The outside is your electron cloud. Protons are positive, and they're found in the nucleus. Neutrons are neutral or zero charge. They're found also in the nucleus. Electrons are negative and found orbiting around the nucleus. Let's see what else. Elements are, everything is made up of elements, and it cannot be broken down any further. And we find all of our elements on the periodic table. When you read a periodic table, the atomic number, right here, tells you how many protons you have. The atomic mass, I'll erase that real quick. The atomic mass tells you your protons plus your neutrons, so you can rearrange that equation or use your atomic mass, I'm going to call it AM, minus your protons to solve for number of neutrons. And your electrons always equal your number of protons when we're dealing with just a normal atom. Then we also talk about the energy levels, where we need to fill in our inner energy level first before we can move outwards. And it's always 2, 8, 8. We also talked about isotopes. Isotopes are elements with different number of neutrons. So our atomic mass is the average. And so we can use these to help us figure out how many neutrons there are. So you just take your atomic mass minus your protons, or your atomic number, or the atomic mass here. Yeah, atomic mass minus your protons, and that'll give you your number of neutrons, just like what we did before, but this time it'll be given to you. Then we have the difference between organic and inorganic. Organic compounds are made up of carbon. So anything that has carbon in it is organic. Inorganic is anything that does not involve carbon, which would be considered non-living. We talked about bonds, which are 2 types, ionic and covalent. Ionic is the sharing or the gain or net loss of an electron at an outer energy level. And again, it has to come from the outside, not the inside. So that's it. I want it, I take it. Covalent means they're going to share those electrons between them. And those are our drawings, so hopefully you drew those in. We can make up a molecule, which is the smallest unit of a compound. So just like how we drew our sodium chloride and our water, those would both be a molecule. And they have van der Waals forces that allow multiple of a molecule or multiple molecules to bond together and hold together, even though they really want to just repel each other. Then we talked about kinetic energy, which is the energy of motion, and then Brownian motion, which is talking about how molecules move and bounce off of each other and stick together as well. All right, so that's all I have for you today. Make sure you fill out that worksheet that went along with the notes. Your homework tonight is Form 2.2 due tomorrow when you walk in. We'll also check your Form 2.1 that was due today, so make sure you get both of those done. And you can also work on any missing work. Please shoot me an email if you have any questions, and I'll try to get back to you as fast as I can. I hope you have a great rest of your day. See you tomorrow.